Good morning. So today what we're going to be doing is we are going to be taking some notes on similar triangles. So we've talked about congruent triangles. Now we're going to talk about similar triangles. And it is the 30th. So with our similar triangles, the first thing we're going to do is we're going to start by defining what exactly does similar mean. So with congruent, we had same shape, same size. So all the angles were the same, all the sides were the same length, everything was the same. Well, similar, it has the same shape and the same angles, but it has different size and it has a different sides. So we were playing around with scale factor last week, and a lot of this has to do with scale factor. And from last week, we learned that when K, which is our scale factor, was greater than 1, it was enlargement. So that means our triangle or our shape got bigger. If K was between 0 and 1, it was reduction. So that means our whatever shape we were, it got smaller. So with similar, you might see this little squiggly line used in the equation. This means similar. Just like that equal sign with the squiggly line meant congruent, just that squiggly line means similar. And something to know about these similar triangles is they are proportional. Proportional. And if I misspelled that, I apologize. So because they are proportional, that means that all the sides have the same K or scale factor for each side. So every single side, no matter what you do, if you do 3 times 2, whatever you do, always going to be the same. So this is a way for you to check to see, okay, are my triangles congruent? So let's look at 2 triangles. And when you draw these, they don't have to be perfect because that's why we have markings. So I'm going to do my first triangle. It's going to be purple. I have one little arc, an arc with a tick, an arc with 2 ticks. I'm going to call it triangle A, B, C. And I'm going to give it a side length of 7 here, a side length of 6 here, and a side length of 10 here. I'm going to draw another triangle, and we're going to try to see, are they similar? So this second triangle, I'm going to give it angles. All the angles are the same. So right now we can be like, okay, yes, this is similar. But there's a way to check. So this is going to be triangle DEF. And I'm going to give it sides of 14, 12, and 20. So technically what we're trying to prove right now, we're trying to prove that triangle ABC is similar to triangle DEF. And just like when we were talking about congruence, the name order rule matters. So we can see, okay, let's figure out, are they proportional? And the way we do that is we set up ratios. So I know how much y'all love factors and factoring. What are they called? Fractions. I got this. Because fractions mean our proportions. So we're going to check to see if they're proportional. So we have AB, and we're going to compare it with what is the same. So AB, so it'd be DE. So we're going to compare them. So we know the length of AB. The length of AB is 10. And we know the length of DE is 20. So I'm just going to reduce it and do a fraction. So I know 10 divided by 20 is going to be 0.5. Or I could also just call that 1/2 if I reduce my fraction there. All right, let's look at another side. So we know one thing, we have a scale factor of 1/2 for these two sides. Let's check our next two sides. So I have BC, and I'm going to see I have BC, and that's proportional with EF. So now let's look at my sides. So BC is 6, and EF is 12. I reduce that, 6 divided by 12, that would give me 0.5, which is the same thing as 1/2. Okay, same scale factor, still checks out. We still have to check that last side just to make sure that it is in fact similar. So our very last side, we have AC, and we check it with DF. So that's the same thing as saying AC is 7, DF is 14. 7 divided by 14 is 0.5, which is the same thing as 1/2. So this checks out, they are proportional. I don't care if you put it as 0.5 or as 1/2. I'm using fractions, so I'm going to keep fractions. If you don't like fractions, use decimals. So we can also use these proportions to our advantage when we're solving. So say, for example, say that we had two triangles. Say we had the triangle like this. And even though these look congruent, that's just because I'm a terrible drawer and it doesn't matter because I'm going to be labeling them anyway. So I know that it's congruent because I have these markings. This one has the same markings. Remember, those ticks on the angles mean they're the same. So far we know they're same shape and the same angles. Well, say we knew that this triangle here had a side of 20 feet here and 30 feet here. And this other one had 50 feet here and X here. We want to try to figure out, okay, what is that X? Well, there's multiple ways we can do this. We want to set up a proportion, and there's lots of different ways to set up this proportion. So I'm going to write 2 of the ways over here so we can kind of look at both of them because you'll get the same answer. And I'm using 2 different colors just so it's super clear. So say I have 20 feet. So I have 20 from my first triangle, and what matches over here is the 50. So I'm going to put 20 over 50, and that would equal, I'm just going to set it up. So 20 over 50, then I'd have 30 over here and X over here. So notice it goes purple, red, purple, red. The purples are on top, the reds are on the bottom. That means that you're setting it up according to what they are corresponding with. Another way you could do this, I could also use the small triangle to the big triangle. So I could put 20, I'm just going to set up my proportion real fast with the blue. So I could put 20 over 30, and then I want to start down here, equals 50 over X. These mean the same thing, they're just different ways for you to set it up. And you solve them both the same exact way. So whenever you have a proportion like this, you can do something called cross multiplication, which you might already know before. The only reason you can do cross multiplication here is because both sides have fractions and it's not adding or subtracting or anything else. That's the only reason you can do cross multiplication. So I'm going to do cross multiplication. I have 50 times 30. 50 times 30, and it would equal 20 times X. All right, I'm going to solve this. 50 times 30 would give me 1,500 equals 20X. Then I need to divide each side by 20. So my X would be, hold on, 75. 75 feet, because those were our units. So you can figure out what is missing just by setting up a proportion. We're going to try another one now. So our second example, example 2. And remember, these triangles don't need to be perfect. Just draw random triangles. That's what I do. I am not an artist. That is very clear. All right. So these are my two similar triangles. I'm going to have this one be a side of 21 and 24. And this one is going to be X and 16. This is why markings are so important. This triangle looks like it's bigger, but in reality, this triangle is. This is why in geometry, you have to prove everything. You can't trust what you see. It's not just because I'm a bad drawer. It's because that's just how it works. So we're going to set up a proportion. So I know something over something equals something over something. I'm going to do this to this and this to this just because for me it makes more sense. But if it makes more sense for you to go from triangle to triangle, you can do that as well. So I'm going to start, I have 21, and it matches up with X on my other triangle, equals 24, and that matches up with the 16 on my other triangle. Now I'm going to cross multiply. I have X times 24, which gives me 24X. Then I have 21 times 16, which gives me, that looks wrong, 336. Yeah, that's right. And then lastly, then I divide. So I have X equals 14. And this one, it didn't give me any units, so I'm not going to make any up. So there's going to be one more type of triangle I want you to look at today for our third example. And it is called a nested triangle. This is the actual term for it. I will call them pregnant triangles because it looks like a triangle with a little baby. So I'm going to draw a big triangle first. So I have my big triangle here, and then there's a little baby in it. So those are called nested triangles, or if you listen to me, they are my pregnant triangles. So the little baby has a side of X and 8, and then the mom has an 18 here and a 16 to the side. So to be able to compare these triangles, the mom has to give birth. And the reason, sorry about this analogy, the reason why is because we need this entire side length to set up our similarity. So I'm going to redraw. I have my baby triangle with an X and an 8. And then I have my mommy triangle with an 18 at the bottom, but the side isn't just 16. You have to add that 8 as well. So the side is actually 24. And now you can set up your proportion to solve for X. So I'm just going to do it super, super fast and with one color because we have done 2 already. So I have 8 over 24. The reason it's so important to redraw it is so you don't put 8 over 16. And then it equals X over 18. I cross multiply and I solve, and you should get X equals 6. So we're going to do some practice on this. Let me know if you have any questions. Okay. Oh my God, I didn't stop recording.